So thank you, Dr. Giles Forestry from EPFL. Happy to have you here. Thank you for keynoting day 2.
Thank you very much. Okay, can you hear me fine? Okay, good. Good morning, everybody. So my name is Gilles Forestier. I'm the director of the HPC platform at EPFL, and I'm also the director of one of the EUROfusion Advanced Computing Hub. And this is what I'm going to talk about today. In particular, I'm going to talk about how those hubs leverage high-performance computing to accelerate engineering in research and engineering in nuclear fusion. Before I go deep into the subject, I will talk about a little bit about a few things that happened over the last year in fusion. So fusion has been, let's say, a sleepy or dormant field in science for a long time. But over the last year, a few things have happened in this area. The first one, which you probably heard about, is the ignition that happened at Lawrence Livermore last summer. So that was done in Lawrence Livermore in a facility that is called NIF, National Ignition Facility. And so what happened there is that for the first time, in this particular case, the amount of energy that was produced by a plasma was greater than the energy that was inserted in the plasma. Okay, so here you can see the amount of energy that was produced, so almost 4 megajoules for 2 megajoules in. I will take the opportunity to talk about this because this is a very important concept. The ratio between the energy that is produced and the energy that is put in is called Q. Okay, so it's I don't know, it's coming from quotient maybe or whatever. This Q, for the first time, was superior to 1, but this for the first time in a controlled way, because having a Q superior to 1 and actually closer to 100 has already happened in fusion 50 years ago, and that was done with an hydrogen bomb. Okay, so in an uncontrolled way, it's extremely easy to get a lot of energy out of plasma. What is really interesting here is that that was produced in a controlled way, okay, in a facility. How did they do that? They shoot lasers at a pellet of deuterium and tritium, I think, so fuel. And so there was an explosion and an implosion, and this implosion actually created a plasma that produced this amount of energy. Something else that you need to understand is that when you hear that Q was superior to 2 here, it's not completely true. This is true for, so it's what we call Q plasma. It's true for the plasma, so the energy that we give to the plasma and the energy that is coming out. But if you factor in all the energy that was used to actually run the facility and everything, this Q is closer to 0.01. Okay, so we are actually very far from having a true net output. But this is absolutely normal. I mean, the facility was not designed to be a reactor or to produce electricity and insert it in the grid. But this is mainly designed to do research for nuclear weapons. Okay, so this is one way to actually, it's called the inertial confinement in technical terms. This is one way to produce plasma, but it's not really interesting for civil purposes. What is more interesting is something that you also might have heard. Earlier this year, the jet tokamak in England actually produced a record of 69 megajoules over 5 seconds. This jet tokamak was closed recently, so that was the last experiment that they did, and they did manage to produce quite a lot of energy. The Q plasma and this is inside the tokamak. Okay, I'll talk about this a bit later. The Q of the tokamak is, I think the record right now is 0.6. So we are not even breaking even in terms of energy production for the plasma. What you need to understand here, I showed this because that's what is quite interesting, is that they produced 69 megajoules of electricity, of power, using 2 milligrams of fuel, which is deuterium tritium. And this is the equivalent of 2 liters of petrol. So 2 milligrams of fuel in fusion, if this ever works, is going to be equivalent or better than 2 liters of petrol. Okay. So now I will concentrate on the tokamaks, and I will concentrate on that. So what is fusion? It's a form of nuclear energy. So instead of splitting the atoms like is being done in fission, the very light atoms are fused together in particular conditions. And this reaction produces helium and neutron, and so a bigger atom with helium and neutron. Okay, this reaction is happening constantly in the sun. That's where the energy of the sun is coming from. It's happening in the sun because there are some particular conditions which are called the Lawson criteria, and they imply a huge amount of pressure and very, very high temperatures. So this particular reaction is releasing a lot of energy and is producing neutrons. So it's considered to be a very, very clean way to produce energy, in a sense that it doesn't release any CO2. Okay, so that's kind of a big deal right now. That's why this fusion is really interesting for reducing the environmental impact. And so it's intrinsically safe. It's safer than fission, in a sense that this reaction is so incredibly complicated to maintain that if anything goes wrong, it will stop immediately. The only thing that can really happen is that the reactor will completely melt down, and you will need to rebuild another one. Okay, there are safeguards, but that's the main problem. The problem of this fusion is that it requires temperatures. So in the sun, I think the temperatures are maybe 10 million degrees when the fusion is happening. This is because there is so much pressure that the fusion reaction can happen at those temperatures. On Earth, we don't have the same conditions, and so we need to increase even more the temperature. So temperatures in the tokamak can reach 100 million degrees. That happened, I think, in the K-Star tokamak very recently. I heard the news a few days ago. So they managed to have 100 million degrees plasma in the tokamak on Earth for, I think, a few minutes. So that was also a record. The problem of those temperatures is that if the plasma touches anything, this will completely melt. In particular, the walls will melt. So in order to contain the plasma, which is charged, there needs to be some magnetic fields in order to avoid the plasma to touch the walls. So those are two types of tokamaks. So this is the normal donut shape tokamak that you probably heard of. it's the easiest to build, and this is a stellarator that has a strange shape in order to have a field that is. So it's more difficult to build, but the field is actually easier to manage. Someone told me that stellarator is actually a tokamak that fell out of a truck, and it really looks like it if you look at the two shapes. Okay, so let me go back a little bit. So in order to avoid the tokamak from touching the wall, so you see this is in pink. You have the plasma, and you don't want them to touch. So you need to have a confinement field. This means that there is a void. There is nothing between, and really nothing. So the space is empty. There's no molecules whatsoever between the plasma and the wall. And this is one of the two issues that we have in this matter is that no matter how well your field is designed, some particles will eventually touch the wall. That's unavoidable, okay? The only way to make sure that this happens as late as possible is to build a huge reactor. So the bigger the reactor, the later those particles touching the wall will happen. And that's why you see those, you probably heard about ITER. It's 6-story, it's a huge reactor, and it's a small one compared to what should be done in order to have proper nuclear fusion. The other problem is that how do you get the heat back? How do you harness the heat and in order to create vapor and have turbines produce electricity if there's a void between the plasma and the wall? Okay, this is happening with the neutron. I will talk about this a bit later. Okay, so in terms of physics and HPC, fusion reactors are extremely complex to build, and ITER, I think, will take 15 years to build. This is quite. It will take. So I think it's going to cost more than 10 billion. Euros is being built right now in the south of France in Cadarache. So fusion reactors are extremely complex to build, and over a career of a scientist or engineers or whatever, you will probably see 2 of them built. So this is extremely long, and numerical simulations are therefore an essential tool in order to help their design. You don't want to build something that will take 15 years and cost billions and billions, and realize that there was a problem in conception, and you have to start over. So this is why the simulations is an essential tool. But it's extremely demanding, so building a tokamak is extremely demanding, both in terms of model and resources. So so here I put all the different fields that are involved in plasma physics. So it's pretty much everything you can think of. And the problem is that you have to couple all of those together. So this means that, for example, if I speak in terms of human life, you have to couple physical phenomena that are decades away together. This is very, very difficult. In terms of HPC motifs, so what was called the dwarfs 10 years ago, you can see that, so I put all the main motifs in HPC here, and their correspondence in terms of hardware. And you see that fusion, like astrophysics, is checking everything. So you need to have a supercomputer that does all of this very, very well in order to simulate fusion. Okay, this is the fusion timeline. I used to have the same picture, but with dates. so 2030, 40, and 50, and I was told to remove them because the things are getting late, and you don't want to show that anymore. So I will talk about a little bit without giving any numbers there. Here are the current tokamaks. Okay, this is JET. That's what I showed you before. And so this one has been closed very recently. This is TCV. That's the tokamak that is at EPFL right now. It's so TCV means tokamak configuration variable. It's a very nice tokamak because so it's very small actually. It's I think it's the box is 1 or 2 meters. But you can change the configuration and the geometry of this tokamak. So in order to have experiment and test fusion designs, it's very, very nice. GT60 is an upgrade of the GT, so GT60 SA is an upgrade of the GT60 tokamak that is in Japan. It was, I think it produced its first light very recently. So yeah, those are the current tokamaks that are being operated right now. The goal is to help design ITER, which is a very, very large tokamak that is designed in France in Cadarache. Is currently being built. I think right now they are a little bit late, but it should be available. So it should be operational within 5 years, probably. It's a huge tokamak, so it's 6-story in height, so this tokamak is designed to produce a plasma with a Q, so a ratio between energy out and energy in, that is roughly 10. Okay. So the community is considering that in order to have a fusion power plant, a Q of 20 is necessary. This is because, and when I say Q20, it means not Q plasma, Q for everything. So all the electricity and energy that is necessary to power the whole facility. This is because there's a lot of things to power in a tokamak. So in particular, there are some. So the field, the magnetic field that is produced has to be powered, and there's a lot in cooling and those kind of things. So fusion will happen on a commercial level if Q20 for the facility, so Q facility is above 20. Right now, if you remember, we are at Q 0.01. So there's a lot of things to sort out before this happens. Here I put an approximation, so orders of magnitude in terms of computational power in order to simulate something like a demo or ITER. So this is a very old simulation that was of TCV that was produced at CSCS actually, I think 10 years ago, so we managed to have a simulation. So this is the edge of the plasma. The one of the most important part is the so this is the here in red. You have the turbulence of the plasma, and the simulation was done with so using around 100 teraflops at the time. GT60 is 100 times bigger than TCV, so there will need to be 10 petaflops in order to simulate. That's what we are doing right now. We are currently working on this. ITER is 500 times TCV, so it will require 100 petaflops, and demo is 5,000 times the size of TCV. It will require more than 1 exaflop. Those are orders of magnitude, of course, and yeah, that could vary. But it's a good approximation of the computational power that is needed. Okay. Now that this is out of the way, let me go into what EUROfusion actually is. So EUROfusion is a consortium of nuclear fusion researchers all over Europe, and Europe in a very large sense. So there are 4,800 researchers, staff and students, 28 members in an institute, and 3 associated partners, and 162 entities all across Europe. It was founded in 2014, and the headquarters is actually in Munich. And the goal of this organization is to deliver fusion energy as soon as possible, let's say. So in this consortium, this consortium has realized that in order to really deliver fusion and to advance the construction of the tokamaks, simulations and HPC is extremely important. So they actually created what is called the ETASC. So it's the EUROfusion Theory and Advanced Simulation Coordination between 14 TSVVs. So theory TSVV is theory simulation validation and verification projects, and 5 advanced computing hubs. So this is the coordination between a lot of researchers and engineers and mathematicians. So the idea is to have physicists that will produce models. Then some other physicists will produce test beds in order to validate those models. Then you will have computational physicists and applied mathematicians to create algorithms that will solve those models, and the computer scientists in order to make sure that those models and the programs can keep up with the standard and the state-of-the-art of HPC systems. This is where the advanced computing hubs come in. So there are 5 of those, and among those 5, there are 3 that are specifically targeting HPC. There is one in Barcelona at BSc, one at IPP in Munich, and one at EPFL, the one I'm currently leading. Those hubs they were formed over what was called the proto advanced computing hubs, what was called the LHT, the high-level support team, which was led by OpenACC at IPP for over 10 years. And the specific goal is to develop efficient and reliable tools, and very, very important, modernize and industrialize the research codes. In particular, so this is how the whole thing is actually working. Those here are the what is called the EUROfusion software standards. This is extremely important. So all the codes that actually go through the TSVV ACH, so ETASC procedure, have an obligation to uphold those standards. Okay. So in particular, what is extremely important for us is that in terms of software engineering, we have version control, coding standards, test-driven, and everything. And this is important because in the collaboration, so the interaction between the theory and and HPC. So the standard procedure is actually we take a code, we look at where the hotspots are. Okay, we extract those hotspots. So because in general the codes are quite huge. It's better to work on something that is much smaller in order to do optimization. And so we extract the hotspots. we optimize them, and we insert them back into the original code. And this is so when we insert them back, there is a testing phase, and this is where the collaboration is extremely important, so that we make sure that we actually did is not going to break anything. In terms of procedure, TSVV, so TSVV have research codes, and they wish those codes to be optimized for a specific target. Okay, so they send requests to the scientific board of EUROfusion, and this scientific board will dispatch the request to the requested ACH. So an example of that is most of the requests that we get is porting a code to GPUs. Thanks to CSCS and a long history of supporting GPUs in Europe, and believe me on that, if you want to port your code, you go to Switzerland. So we are getting actually, so my hub is getting twice the amount of requests that I can actually afford in this respect. So when we get those requests, it's very important that we coordinate with the other ACH to see if we can find some synergies between all the hubs. An example of that is so sparse linear algebra and solvers. You don't want every hub to reinvent the wheel every time there's a request to have a solver ported to a GPU. So we work together in order to come with a common library and software development. The other thing that is very, very important is that the ACHs are in contact with the vendors, so the hardware vendors. For example, my ACH has a lot of contact with NVIDIA. So NVIDIA is helping us a lot in order to develop, in particular, the good example is the sparse linear algebra. We are working a lot with NVIDIA in order to have to use their MGX solver on GPUs. Okay. So yeah, that's the procedure of how things are being done at the ACH. Now I will go into the codes a bit more deeply. So yeah, this is so here are all the codes that we have that we are in charge of at EPFL. Those codes, so in general, when they arrive, so they are mostly running only on CPU. So yeah, I put C and C++ here, but yeah, so most of the 90% of the codes are in Fortran actually. And when I say Fortran, I'm not going to put a version. It can go from Fortran 77 to what is the standard right now. So packed together into a same code. So those codes have been developed for a long time. It's very difficult sometimes to do real development into it. So that's why extracting the kernels is absolutely mandatory for us, because we don't want to touch anything else in the code. In particular, because those codes are still under active development. So having version control and everything is also extremely important. You don't want to break anything in the main code, because this means that researchers cannot do their job anymore until this is being fixed. So it's a very, very difficult task, and really having collaborations between all the hubs and the TSVVs is extremely important. So this is general porting rules. This means that that's what we are asked to do. There are three main requests. The first one is that obviously people don't really like that you touch the code too much. So this means, for example, changing the data structure is kind of difficult, and sometimes it's absolutely necessary if you want to do HPC. So yeah, so they ask to have the least amount of modifications, maximum performance, so as fast as possible, so in the end, And of course, portability, because so the researchers don't really want to be tied to a specific target. Those can be very contradictory in themselves. It's very difficult to all of those. In particular, performance portability, I've never seen anything like that. So performance and portability together. There are three main approaches to actually do that. So the first one is the out-of-the-box performance experience or whatever. So using a library. For example, Cocos, PETSI, MGX, I mentioned this, Blast, LAPACK. So you plug this in the code and you get very good performance. I'll show an example of that. The second one is really developing close to the hardware. So using CUDA, ROCm, Cycle, whatever. And the one that is the most preferred in the community is to use Pragma directives. In particular, so OpenMP offload or OpenACC. I put a color, so you can mix and match those. I put a color to the codes that, so the corresponding color to the codes that we have, and you can see that Pragma directives, and in particular, a lot of people are interested in OpenMP offload. And yeah, you see that there are five codes that actually are using OpenMP offload or OpenACC in our hub, in conjunction with some form of libraries. So in particular, the sparse linear algebra and iterative solvers. Okay, this is done. So I will show you two examples of those codes, and they all have so they are related to edge, plasma turbulence, and particle tracking. So the first one is GBS. It's been developed by Professor Paolo Ricci at EPFL. This code is designed to study the plasma turbulence in a tokamak boundary. So this is a critical part, as I mentioned before, of the plasma of the tokamak, because you don't want to have the plasma touching the wall, at least not too much. So it's a fourth order Runge-Kutta algorithm. So it's using a fourth order Runge-Kutta algorithm for time evolution, and a fourth order finite difference scheme for spatial discretization. It's written in Fortran with MPI. And so we use the CUDA in order to do the stencil computation, so the plasma computation. And the dependencies are MPI, of course, HDF5, PETSI, and CUDA. Okay. The main bottlenecks, and okay, so let me go to this. This is a representation. So in blue, you have the performance of TCV, so of GBS when we got the code. So this is the strong scaling of, in blue, the strong scaling of GBS when we took the code. So it doesn't scale at all. Well, it didn't scale at all. Main reason for that is that the solver was a direct solver, UMF pack. And this is well known that at some point, so UMF pack and direct, so LU factorizations don't work very well, so don't scale very well, okay? So when I asked the developers why they use the direct solver, they told me, yeah, but that was there, we used it, that's it. Okay, so the first thing that we did is to remove UMF pack and the data structure and everything, and use PETSI. So instead of having a direct solver, we used an iterative solver, and you can see in red. So immediately, what happened is the scaling became really excellent. Okay, we got out of the box using PETSI, so going from direct to iterative solver, we got a 65x performance. Increase over 32 nodes. Now we are, I think we are on around 500x in terms of performance increase. The second step was to introduce a GPU implementation, in particular for the right-hand side. This is where the plasma is actually computed, and for the solvers. So we use the PET-C or MGX. So now we are using PET-C and an extension of it, which is called ITER, I think, which is working fairly well on the GPU. So this is how we ported the code to GPUs, and the outcome of that is currently this code. So GBS has an overall allocation in HPC systems, so in particular in EUROHPC and CSCS of 500 million core hours and 5 million GPU hours overall. This is the number of core hours. So CPU only is going down, and we are increasing the amount of GPU hours that we are getting all over EUROHPC. So this is so that's the current development that we have for TCV, and this is a comparison between so time to solution between LUMI and Leonardo. So this is a TCV simulation at 0.9 Tesla. Those are the so this is the size of the grid, and we do 100 plasma steps. There is no neutrals. I will talk about this. The neutrals are right after this. So right now, Leonardo is between 2 and 3 times faster than LUMI-C. The problem is that, so that's when I say 2x, it's really node-to-node comparison. So Leonardo has 4 A100s per node, and LUMI-C has only a CPU. So it's a CPU 128 cores, I think, AMD. So this is not really impressive in terms of performance, because GPU should be much faster than this. Okay. The reason for that is that not all preconditioners and solvers are available in the current implementation of PET-C or MGX. In particular, the preconditioners that we are using for the CPU-only version are not available for GPUs. So so we are waiting for so NVIDIA and whoever is working on this to actually develop those preconditioners. And when we got those, this performance should be much better. Okay, I told you about a little bit about the particles that are going around the plasma in the tokamak. So this is extremely important to simulate because in spite of the fact that the plasma is at around 100 million degrees inside the tokamak, some particles are still neutral. This means that they do not follow the magnetic field that is supposed to be containing the plasma in the tokamak. So this means that they will hit the wall, okay? They will rebound on the wall, they will be absorbed by the wall. And that means that, in particular, they will go back to the plasma, and the plasma temperature will go down. So this can be as bad as stopping completely the reaction, so stopping the energy production. Because of the fact that we have optimized the code, we have resources in order to insert more physics. And the first thing that we did is to have this neutral particle tracking module inserted in GBS. So tracking the particles, those particles in GBS is done using the method of characteristics. And we consider every possible trajectories, and we compute the probability that the particles will either recombine with and create, so plasma recombines and create neutrals, or the neutrals are ionized again, creating plasma, or hitting the wall, or I don't know what, okay? The problem is that this leads to a fairly dense system to solve. So it's not completely dense, but it's not completely sparse either. So we are kind of in a gray zone, and we don't really know right now how to solve this properly. Anyway, so we took the module that was already existing in GBS, and we optimized it through certain techniques. So this is the scaling of the plasma, neutral computation in GBS. So right now, you see it's perfectly scalable. This was done on SuperMUC NG, I think. So you see that up until 128 nodes, the scaling is absolutely perfect. Here I put a test case of a simulation. So you have the size of the plasma grid and the neutral grid, so with the interpolation, and this is a smaller one that should be used for because TCV requires a 100 times 200 neutral grid. The problem of this is that the neutral computation, even if it's optimized, so here you see that one neutral solve takes much longer than a plasma iteration. This is going to be very difficult to optimize. There's really too much that, I mean, optimizing this number is going to be very difficult. So what we do is that instead of having so this is the normal way the computations are done, and you see that's the plasma, okay, and this is the neutrals. So you see that most of the time will be spent in the neutral. Plasma will be 0 compared to this. So what we do is that we subcycle everything. So we run the plasma and the neutrals in parallel. So we have two communicators in order to do that. This reduces the simulation world time at the expense of more resources, obviously, because you need to have twice or more than that you actually have here. But we can overlap the computation of the plasma on the GPU and the neutral. So what we are working on right now, and I think the Gray Super machine at CSCS could be very nice for this, is to have on the CPU the neutral computation, and on the GPU the plasma computation. Right now it's separated, so there is twice the amount of resources. So that's what we are currently working on. Okay, the second code actually does the code that I was in charge of, even when I was working at the high-level support team. Is the longest code I've been working on, actually. It's called ASCOD 5. It's being developed at the Aalto University in Finland. And it's really a particle orbit following for the toroidal magnetic confined fusion devices. It's a Monte Carlo method, okay? So it's really tracking the particles and the evolution with those functions. And this is the discretization, so the approximation. And they manage collisions with the static Maxwellian background plasma. Here you have a picture of this is ITER, I think. This is a reproduction of ITER, and you can see the particle, so when they hit the wall, the amount of energy that I think it's the energy that is produced. This code was developed originally for Night's Landing. It's very, very well coded. It's a C code, MPI plus OpenMP, that's it. It's highly vectorized. It's really beautiful in terms of HPC engineering, okay? So this is how things are being done on the CPU. So if you know a Monte Carlo method, you know that all the particles, so the tracking are all independent. So it's perfectly parallel in a sense. So meaning that each particle are independent from each other in general. there are two levels of parallelism. The first one is MPI, with the fields, so the magnetic fields, replicated over the nodes. And inside the node, they used OpenMP with a queue-based approach. So this work stealing, where as soon as a particle dies, the queue, the CPU will get another one in the queue, and so on. It's highly vectorized using SIMD, and it worked really, really well on the KNL, which does not exist anymore. But the code is really well written. It was very nice to work on this. So what we did is, in order to port to GPUs, we changed a little bit the structure. So instead of having the SIMD, threads, vectorization, and whatever, we inserted we inserted the OpenMP offload paradigm. So I put it here. This is the execution model of OpenMP offload. So that's 4.5. I think it's still correct for 5.0. And so this is based on, you can map the hardware to to the loops using those pragmas. Okay, so in general you have 3 levels. Here we have 2. So this is the main loop of the tracking of the particles, and so we have the teams. The queue is so the marker queues is distributed over the OpenMP teams, and each marker is distributed over OpenMP team threads. So here, so those 2 here is. Okay, that's the first thing that we did. It was extremely easy because we just had to replace the normal OpenMP, so pragmas, to insert the teams, and yeah, that was fairly straightforward. Okay, so this is, we were expecting very, very good results of using OpenMP offload, because since the particles are all independent, should be working very well on the GPU with a lot of threads, but the problem is that this is the first results that we actually got. So Helvetios and JEDS are the CPU-only machines that are currently at EPFL. So this is the benchmark that we are competing against. You can see that this is Marconi 100 at Cineca. So it was an IBM Power 9 plus V100 machine. OpenMP offload was producing good results. But compared to a CPU only, so you have one CPU and one GPU, V100, which is fairly good, still a fairly good GPU, we were expecting much better results. Okay. The real problem was, so Phoenix is our test system at EPFL, and so it's using GCC V100, so same as Marconi 100, and the problem is that we got really, really bad results. That was extremely surprising. But we also inserted, so we tried with OpenACC, and the results were fairly decent, so comparable to what we had with OpenMP offload on Marconi 100. Okay, so it took us a long time to understand what was the problem with OpenMP offload and even OpenACC to some extent. We were expecting much better results compared to CPU. So what we did is, the first thing is that we moved our implementation to either, something that either uses OpenACC or OpenMP offload. This is extremely easy to do because those two, so OpenMP offload and OpenACC, are fairly similar. So this means that you just need to change the names of your pragmas, and that should be that is working out of the box. Okay, so with this, depending on the flag that you pass to GCC, so either minus OpenMP or minus F OpenMP or minus F OpenACC, you will have an implementation that is using either OpenMP offload or OpenACC, and it works. It works really, really well. The second thing is that, and this is the heart of the problem. The second thing that we did is that we needed a new algorithm. So the problem of performance that we got with this original implementation is that it was really, the code was really designed to work on the CPU. So this, design on the CPU. The problem is that on GPU, with OpenACC or OpenMP offload, this is producing a huge kernel, a huge CUDA kernel. I checked one of the test cases. One kernel was using 1,500 registers, which is way too much. So this means that there were not a lot of threads or in flight on the GPU, and so yeah, we needed to change this. And in order to do that, we had to find an old way of doing Monte Carlo, which is called event-based. So here, if you want, one SIMD lane is in charge of the whole lifetime of a particle. And when I say whole lifetime, it means that the particle will go through a series of events, so either dying on the wall or collision with another particle, whatever you think about. Here, we decided to use this event-based approach, meaning that we don't parallelize over the particles, but we parallelize over the events. So this means that in the end, we have much smaller kernels, which are much more suited for GPU execution. And immediately, you see the performance increase when we coded this. This is a comparison of, so I have two benchmarks, 1 million markers or particles and 10 millions. And this is the scaling performance, or strong scaling, from 1 to 32, either nodes, if you're on the CPU, or number of A100. Here you can see that one A100 is, I think, 3 times or more than 3 times faster than one node of JED, which is Ice Lake with 72 cores. So one A100 is 3 times faster. Here on the 10 million marker, and here I put the NVIDIA, so Grace Hopper, which we got access through an engineering sample thanks to NVIDIA. You see that one node, one H100 is more than 6 times faster than one node of CPU, so Ice Lake, which is a very, very good, yeah, this is, I think, is the second best that we have at EPFL. So very, very good performance. And so this is much more what we expected in terms of performance on GPUs. And what is also very nice is that going from, so when we went to Grace Hopper, the node of Grace Hopper, we didn't have to modify anything. We just compiled the code, we ran it, and that was it. Even if it was a completely different architecture, we got performance out of the box. So this is as close as it gets to having performance portability, in my opinion. And yeah, we are very looking forward to getting access to the HUBS system, because this is really promising for us. Okay, yeah, conclusions. So EUROfusion, as I mentioned, has created a framework to improve high-performance computing scientific software to help build fusion reactors, and in particular this collaboration, this coordination between theory and optimizing the research codes. through the EUROfusion coding standards that are extremely important for EUROfusion. And this allows us to get more resources, do more simulations, and insert more physics in the code. And the port to GPUs is done in several ways. Our preferred way is to use OpenMP offload and OpenACC directives. It gives the best portability for us. Unfortunately, they are not available everywhere, but we found a way to go around that. And that's how actually the hubs are leveraging high-performance computers to accelerate fusion power plants delivery. Thank you very much. I'm right on time.